So what are these things which we call defects? And you might have already heard of some of the examples of defects which you might be aware of. One of them is vacancy, and then there are some other like Frankel defect, and there can be a defect which is in one dimension, and there can be defects in 2 dimension or in 3 dimension. So these are vague terms. When I say something is in 1 dimension, then in a 3-dimensional space it is hard to have an entity which is in 1 dimension, right? Because we are talking, so when we say it is only in 1 dimension, then that means it does not have any thickness, it does not have any cross section, it has only 1 dimension, length, or whatever you want to name it. So these are relative terms. If the other dimensions are very, very, very small in comparison to 1 dimension, then we can say that the other dimension do not exist or insignificant. So, but they are there. If we go to that level of measurement, then it is hard to avoid that things are actually in 3 dimension and not in 1 dimension, and sometimes no dimension at all. But still we name those things. So let's talk about vacancies. We know that vacancy is a defect, but it depends on our definition of defects. So our definition says that a crystal is perfect when all the sites where the atoms should be are taken by atoms. And when that happens, we call that a perfect crystal. But it is ironical for our understanding, and although our all understandings are based on such definitions, that a crystal is perfect, for instance here, when all atomic sites are taken by atoms. But it doesn't happen in reality, never. We can never have a crystal system which has all the atoms on its sides. So we can never achieve any crystal which is perfect. Although according to the third law of thermodynamics, it should be available at absolute temperature, which also we cannot achieve. So if we cannot achieve this, we cannot achieve that. So maybe our definition of calling something perfect, we could call it absolute, because absolute things are not in reality, they don't exist in reality, they are unattainable. So you can change your definition of perfect, and you can imagine that unless you have an atom missing, at least one of the atomic sites are absent from the atom, only then the crystal is perfect. Then we will see almost all the crystalline materials in their perfect form, in their natural form. But it is just so that our definition of perfect does not match with natural or naturally existing. So somehow whatever we see in nature, we say that those things are not perfect, and there is something absolute, something perfect, something heavenly can exist at some absolute temperature, pressure, scenario, or place. But by nature, it is important for a defect to be present, and therefore defect, although sounds a negative term, it sometimes provide a lot of ways of things that are there in the universe of materials. So we will talk about one particular type of defect today, and there is a reason why we need that. So let us imagine that we have a perfect crystal and all the atomic sites are having atoms sitting in their equilibrium position. Okay, and so we have atoms like this, and then we have another atom layer, so maybe like this. Okay, and the distance between these two planes, so this appears to be a plane of atom, and so this interplanar distance, we can call this A, and the interatomic distance, we can call that B. Okay, and now, so if this is the situation that we don't have any defect and we are trying to deform this material, and this is my x direction and this is the direction, so this is x1, this is x2, and along this I'm trying to apply a stress, and this stress, because of such arrangement of atoms, will vary from the because of the presence of atomic sites, right? And so let us say that our strength, which in this case we are calling cohesive stress or cohesive strength of the material, let's say that it changes in a sinusoidal behavior, so maybe something like this, and then it can go like that. Okay, and so this may be the initial position for this wave, let's call that A naught, and the amplitude of stress goes to a maximum, which is sigma max, and the wavelength, half wavelength, is given by lambda by 2. Okay, and so we can say that our stress here follows a sine curve equation, which can be given by the amplitude multiplied by the sine of the angle, and that angle at any point of time can be given by this 2 pi by lambda into x, right? Because the whole wavelength covered in 2 pi degrees will be lambda, so any unit distance will be 2 pi by lambda, and the unit dimension along x1 direction, so nothing is happening, actually no displacement is happening in the x2 direction. That is our assumption, so we can just call it 2 pi x by lambda instead of calling it 2 pi x1 by lambda. So this is how the stress changes. And if we imagine the angle to be very, very, very small, then we can take sine of theta is equal to theta, so we can say sigma max 2 pi x by lambda, right? And now we can say that stress is actually following Hooke's law, because we are talking about elastic deformation. So this should be elastic modulus into strain, and strain in this case is actually x by A naught. So this was the original dimension, and then because of the stress you move the atom in that direction, in x direction, by a amount x, right? So the strain can be taken as delta L by L, so that will be x by A naught. So we can write stress to be equal to Ex by A naught. Okay, And then this A naught, if we imagine that this A naught is actually half of the distance between two atoms, if we imagine, because these dimensions are very small, so we can imagine or assume that this is equal to the half of the distance between two atoms. So then we can say, sorry, not here but the whole length. So we actually say that, so the atoms will be sitting at lambda wavelength, right? So the distance between half will be lambda by 2. So we can assume that A naught is equal to lambda by 2, and this is our assumption. And this assumption is not very wrong, because we are talking about dimensions of very short lengths. So we are not making much mistake here by having this assumption. So now we can replace A naught with lambda by 2, and then we can plug everything back in the original equation, and we can say that sigma should be replaced by Ex by A naught is equal to sigma max and 2 pi x by lambda, and lambda is 2A naught, so we can replace lambda by 2A naught, right? So then this gets cancelled, A naught gets cancelled, x is cancelled. So what do we get? We get sigma max is equal to pi by E, right? So this is what we get. And now, so this is the maximum value the stress can attain if we want to deform the atoms elastically, and we imagine that it is a perfect crystal, there is no defect. So what happens is, how much strength is required to have, this much amount of strain, So this is the maximum value of stress it can go to. And for most of the materials, especially let's say steel, for steels, the elastic modulus is in the range of 200 gigapascal. For titanium alloys, it is in the range of 100 gigapascal. For aluminum, it is 70 gigapascal, close to that. Okay, so there can be a change of 2 megapascal or 1 megapascal, which will make it 201 gigapascal, 202, 205, sometimes 210. So we are not making, so this in this range steel falls, in this range titanium elastic modulus, and in this range aluminum and their alloys. So let us put 200, which is the highest. So if you put 200, then how much should be the strength you will be getting? So this will be 3.14 divided by 200 gigapascal, right? Oh, there is a mistake here, because dimensionally it is not correct. So sigma max should be E by pi. So this will be 200 E by pi. So this will be 200 by 3.14. And so so let's take that to be 3. So how much that should be? It should be 6 and then 66 point something, right? So 66 point something, 66.7. So we get 66.7 gigapascals of strength. But maybe many of you know, or maybe not, this is a very high value. You don't actually need this much amount of stress to break steels. You need much lower than that. So if you take the very, very smallest value, so 70 by pi, which we are rounding off to 3, will be 23.3 gigapascal, and this is also very high. So the question is, what is wrong? If we calculate the stress to be in gigapascals, we actually don't see even any material close to 1 gigapascal. If you go to, so the closest you can get is for Mar aging steel. For Mar aging steel, you need very high amount of stress, maybe close to 1 gigapascal to break it, but not any other material can go to this much amount of strength to break it. So then what is wrong in our calculation? Not even breaking. So breaking, forget about breaking. We are talking about deformation. And we need much lower amount of stress in order to make deformation in steel. So what is wrong? And if there is something wrong here, then it is right to say that material is not deforming in this way. Okay, so let us discover on this in the next page. So now we know that materials deform at a very low stress in comparison to what we calculated is called the theoretical strength of material. Theoretical strength of material, or the theoretical cohesive strength of material, and that comes out to be E by pi. Okay, so, and this is comparable to, so E you can relate to G by 2 into 1 minus mu, and mu is not very large, so you can just ignore it. So this could be G by 2 pi, where G is the shear modulus. Okay, so now we know that this is not true. We never attain this much amount of strength, so there is something wrong. The mistake what we are making in this theory is that in order to have one atomic distance of deformation, so let's say that this is how our atoms are arranged. Okay, and we are applying a shear stress like this, and a shear stress of the same amount in that direction. Okay, now you increase the shear stress in this direction, then it should deform. Okay, or you fix this direction and just apply shear stress in this direction, then it should deform, right? And now we are saying with this theory that, so this is figure 1, and in figure 2 we are trying to say that the displacement or this deformation which is happening in our material is of one atomic distance. So it's like this, and this is happening, and so this is x1, this is x2, and then you have x3 direction like that. So you have atoms in along x3 directions also. So you have something like this. Okay, so you have something like this in 3 dimension, and what we are saying here is that the whole plane, this plane of atom, okay, so this plane of atom, the whole thing up along this line has moved in one instance. So if there are 100 atoms on this plane, all those 100 atoms have moved to this position. So this atom has moved here, this atom has moved here, this atom in x3 direction has moved here, and so on. And this assumption is wrong because it requires a coordinated movement of atoms along the whole plane, and so that requires a lot of energy, and that we know because the energy barrier for this atom to go there will be of some value. So let us say if there is a stability, so there is a stable phase here and there is a stable position here, and this is the free energy. Then in order to go from this place to that place, so this is my atomic site number 1, which was here. Okay, so this is site 1 and this is site 2, and the atom is going from here to there, and it requires some amount of energy, which is a barrier. It will just not go there because it will have to increase its energy and then go there, and this is called the energy barrier, right? So this is my energy barrier, and this energy barrier for one atom is something, and for n number of atoms it will be multiplied by n, which is a huge amount, and because of that we only get a very, very high value of stress required to do this much amount of movement. And so it appears that material is actually not deforming in one go. So the whole thing is not moving in one go, right? Not only that, we are also saying that not only this atom has moved there, also this atom was there. So this has also moved, this has also moved, this has also moved. So we are actually saying that the whole slab of material has actually displaced itself in coordination with millions of atoms in one go, and that's not happening. So then what is happening? So the theory which describes the phenomena in reality is based on the concept of dislocations, and that's the kind of defect we are trying to understand in this lecture. So what is explained by the theory of dislocation is that we have a defect in our system, and it is there, it is just there by nature. And this defect can be described that at some plane atoms are missing. So you can say that this plane of atom, so instead of saying atoms, and this again is, let's say, x1 direction, this is x2 direction, and the plane which is, so the direction which is going in the plane is our x3 direction. Okay, so we have a whole plane in x3 direction, and this plane is not here, it's missing, right? And then when you apply stress, what happened is that this plane has joined this plane. Okay, and now this plane is, so this has joined this, and so this plane is now not having the partner down this line, right? So we have now moved by one atomic distance. So the missing plane was here in the column number 2, and now the missing plane is there in the column number 3, and in the next step this will be in the column 4, and you will get this one step. So imagine this to be the surface. So in the next step what will happen? This will happen. So now this will join this one, and so on the surface you will see a step. Okay, and this phenomena of movement of such kind of dislocation is called, and many such steps together when you see, is called a slip band. Okay, many of these kind of steps together are called slip band. So now let's pause for a while, and what we learned in our last page uh, was a mechanism of deformation in which atoms move piece by piece together, and instead of drawing those atoms, we can draw planes. So we can say this is the plane, and then this is the plane of atoms, and then there is a plane which is missing, and then there is a plane, and then there is a plane, like this. So this is how the material is, and the atoms are like this, arranged at their interatomic distance. Okay, so instead of drawing all the atoms, we can draw planes, and we can say that this plane is missing, right? So this plane is missing, and this becomes a symbol of dislocation. So this is a symbol of dislocation, and this particular type of dislocation. So now there are things which we need to understand about this. So what is happening here is that this plane is joining this, and this part becomes free. So this part becomes the extra half plane. Then this extra half planes join this one, and this one becomes extra half, and then this joins this one, and then at the end you see an extra half plane there which forms like a step. Okay, so instead of moving all the planes in one go, you are actually moving piece by piece. Okay, and you see that it is not required for all the atoms. So now this is my x1 direction again, and this one is x2, and this direction is x3. So I will obviously have atoms along x3 direction, and so I'm not saying that all these atoms. So when I say that this plane have joined this one, so let me do that with another color. So when I'm saying that this plane is joining this one, it is not required for all these atoms to switch to this one, right? The phenomena can also happen in x3 direction piecewise. Okay, so now let us try to see that. I hope I can make you understand by drawing this. So now same drawing I'm trying to draw in a different way. So imagine that this is my half plane. Okay, so I have atoms along here, and this is my x3 direction now. Okay, and so now when I say that this half plane will join this, and here I have atom and here I have atom, right? So now this joins this, so that this part becomes free. So instead of all these four atoms joining this layer of atoms, it can happen in the next step. Let me draw that part. It can happen that this plane has joined, so a little tilt I am making here, so to present that this half plane has joined that one. Okay, this half plane has joined that one, but in the next layer along x3 direction, the half plane actually lies here. And so let's denote that here my x3 coordinate value is 0, here my x3 coordinate value is 1, and here my x3 coordinate value is 2, and so on. Okay, so one atomic site has a unit of 1. What I'm saying here is that x3 is equal to 0, the half plane has moved. x3 is equal to 1, half plane has not moved. x3 is equal to 2, also not moved, and it has happened only on the first layer of atoms. Okay, slowly it will happen to the second layer of atom, and then to the third layer of atom, then to the fourth layer of atom, and so on. And the same phenomena on x1 x2 plane is also happening piecewise. So it is a piecewise phenomena. Not more than one atom are required to move in one go, and therefore this phenomena needs much lesser amount of energy in comparison to the theoretical strength, and therefore this explains that why material can deform at a very low value of stress. So this phenomena is called slipping. And it is called slipping because it looks like one layer of atom is just slipping on another layer. It looks like this. It looks like the upper part, which is 1, has actually slipped in the right hand direction, and that's why it is called slipping. Okay. Now what is important here is that in this mechanism, the displacement which happens on the atomic level, so the displacement is always one atomic distance, at least. Okay, at least it has to be one atomic distance. It cannot be less than one atomic distance because that is not possible thermodynamically, right? Atom cannot move by a fraction of distance between. So this atom cannot move between. So if two atoms are sitting at their equilibrium position, a position here is not available for any of these two atoms. Okay, so it has to move at least by one atomic distance, and there is a geometrical description of this thing. Okay, so now let us take again this drawing of dislocation moving, and we will try to take a path around atoms and we will try to see what is happening. And in this diagram I will have to draw atoms again. So let me first make the atoms and then we will say what is happening. Okay, so you can see where the dislocation is, where the half plane is. Let's not talk about dislocation because it might be confusing for many of you where the dislocation is. We have also not yet explained what a dislocation is. Okay, so we will stick to half plane, a missing plane and an extra plane kind of explanation. So now try to see. So this is the extra half plane, right? And it has atoms also in the x3 direction, and for x3 direction I am not drawing anything else. So just imagine that this is how it is, right? And now we will take a path which goes equal amount of atomic distances in each direction, and I want to start from any position and I want to come back on the same position because that should happen, right? That should happen in a perfect crystal. So I start from here, then I go 2 atomic distances. So I go 1 here and 2 here. Okay, then I have to go same amount of distance there. So I go 1 here, 2 here, then I go 1 here, 2 here, then I go 1 here, 2 here, and now I'm not at the same position. If I do this thing in a perfect crystal, I will always come back to the same position, right? But in this case it is not possible, and so a missing distance is one atomic distance, and this distance is called, it is the amount by which this half plane has moved, and this amount or this direction is called the Berger's vector, denoted by B. Okay, so this is a vector and the name is Berger's vector. Okay, and so the magnitude of Berger vector here is 1, right, and the direction is the direction of the movement of this half plane, right? But where is the dislocation, and what is a dislocation? So dislocation is this line, okay, this line is called dislocation, and it starts from here and it will end when the atomic structure ends, right? And in a real material, the atomic structure ends where? Either at the surface or at the grain boundary. I'm not sure if you are aware of what a grain boundary is, but a grain boundary is kind of a border, you can imagine, between in crystalline structure you have certain areas which has orientation along certain direction. So it is similar to change in coordinate system. Okay, so we'll come back to grain boundary when we discuss grain boundary in more detail. But you know, because atoms are sitting in a crystalline structure and they are everywhere, this arrangement breaks only at the surface or at the grain boundary. Okay, or at a node, and we will talk about node in a while. Okay, so a dislocation cannot end inside a grain. That cannot happen because it's a geometrical entity and it is there as long as atoms arrangement follow the same arrangement. Okay, so I hope it is clear to you that this is the dislocation line, and dislocation line is along this direction, right? Is along x3 direction, because that was our x3 direction, and the Berger vector is along this direction, right? And when this happens, so this line is actually, it's like, you know, if I keep this pen like this and this whole pen is moving in this direction. Okay, so this whole line is moving. So I hope you can imagine how that is happening. So this type of dislocation where the line is perpendicular to the Berger's vector is called edge dislocation. Dislocation, as the name suggests, it's a dislocation in the crystal structure. Okay, things have dislocated from their place. That's what happens here. When it reaches the surface, you see a step, and that's a dislocation. Okay, and this is an edge dislocation because it has an edge here and it makes an edge again at the end. And this type of edge dislocation is resembled by this symbol. Okay, so this will be the case when I have extra half plane above. I can have another situation when I have extra half plane down. Okay, and these two edge dislocations are said to have different poles, okay, or different signs. So if you call this one positive, you call this one negative dislocation. And there is an importance to this because, you know, now you can imagine that this is a half plane on the upper side, and if you have a half plane extra on the lower side also, when they meet, what will happen? It will just be a perfect plane. right? Because here half plane is missing, there a half plane is missing, and you just add these two and there will be no dislocation at all. It will be a perfect crystal. So this plus this will result in no dislocation. Okay, dislocation will just vanish. Okay, so this is an edge dislocation. This is a positive edge dislocation, this is a negative edge dislocation, right? This is how we define it. And then there are differences also, because you have an extra half plane of atom here and that ends here. Below this you don't have anything, right? So this atom, because it is present here, it will try to move these atoms away. However, what is happening in this area of atoms, that they do not feel a need of an extra plane because they don't have it. So because there is an atom there, they want to compress it. Okay, so this dislocation end has a compressive field on this end, and the opposite will be true on the negative dislocation. Okay, so the stress field at the tip of the dislocation has opposite nature when they change the sign. Okay, so now you know that these two will have certain kind of attraction towards each other, because they appear to decrease their energy by just vanishing the dislocation. So they will have certain amount of attraction towards each other, and if you have two dislocations of same sign, then you will have a repulsion. Okay, and this is like electrons or positive charges or negative charges, but this is happening because of the stress field. So because you have compressive stress field here, if you have another compressive stress field, they cannot take care of each other. They will actually repel. They cannot exist at the same time. But if you have a compressive stress field and a tensile stress field, they will actually cancel out. At least a part of their stress field will be cancelling out, and because of that they will have certain amount of attraction. Okay, can you also see something? But this diagram is now too complicated, but let me draw that again, and just the relevant part here. So you see this half plane is here and it is missing in the downside. So now can you try to visualize this? If suppose all these are iron atoms, okay, all of these are iron atoms, and then I put a chromium atom here. So what will happen? This chromium atom will make this plane longer on x3 is equal to 0 coordinate. If I have another chromium atom at x3 is equal to 1, then again this plane will feel to be till this point. But if you go, so I have only two chromium atoms, but on the third, so x3 is equal to 2, on that coordinate I don't have chromium atom, so my half plane is only till there, but here my half plane is until here. And if you can imagine, dislocation line which was initially like that now has become like this. Okay, and we will talk about this phenomena. This phenomena blocks a dislocation, and we will see why. Okay, so this was an edge dislocation. Okay, understanding edge dislocation was easier, But the other type of dislocation which exists, explaining that and visualizing that is a little hard. But still, I will try to make you understand how it is, because this particular type of dislocation is a little different from others, which is only, the other type is only edge dislocation. Okay, so, and what is happening here is, so I hope it is, but it may not be so clear to you. So actually it's like this. Okay, so this has a step in x3 direction, so along this direction. Okay, so it's like tearing action. It's like, it's, so the edge dislocation can be shown by slipping of two slabs, right? So if this happens, this slab slips in this direction, so this is like an edge dislocation movement. Okay, but if you have two slabs initially like this, okay, initially like this, but then because of the, so it was like this, right? But because of the stress now, what has happened is, it has so the downward has, so you have just a little bit of tear, you know, like a deck of card you shuffle like that, it's like that. Okay, so this is a different type of dislocation. Okay, and in this case, the direction of the dislocation Burgers vector is in x3 direction, and the line of dislocation is also in x3 direction. Okay, it appears tilted here, but it is in the same direction. Okay, it's downward because I have a step there, but the dislocation line as well as the Burgers vector, so along the direction where the atoms have displaced themselves, is in the same direction. So Burgers vector is parallel to the dislocation line, and this type of dislocation is called screw dislocation. Okay, and you can imagine this by just taking the deck of cards and try to expand the deck of cards in your hand, and you will see that so the deck of cards, when all of them are like this, and when you expand them along by your finger, then they can look like this. Okay, and the lower one is something like this, and then something like this, and then, right, and each of this, you can say, is the displacement which has happened in one atomic displacement, and that's how the screw dislocation moves. Okay, so the dislocation line and the Burgers vector, so it is actually moving in the plane of the paper, so perpendicular to this paper, right, and it is going downward, so it's like a helix which will go down. which will go in the plane of paper. So that is the direction of Burgess vector. And this is the line of dislocation, which is parallel to each other, and therefore, and so it is a screw dislocation. Okay, so these are the two types of dislocations which we have in the material. And dislocation you can also imagine to be a layer of flowing. So like you have a laminar flow of liquid, and you see that the upper layer, you see the layer moving, right, with a boundary. You can see water on the ground flowing. Okay, so if you imagine a laminar flow, then each layer may be flowing at a different velocity because each layer will have different friction, right? So this is layer number 1, this is layer number 2 of water. Okay, and or wax of very viscous material. So in viscous material you can imagine that one layer is ahead of the other layer, and so this line here, this boundary of the downward layer 2 has moved ahead of layer 1, and that boundary by which the layer 2 has moved ahead is the dislocation line. And you can see this type of dislocation line when you see the material deforming in a microscope. Okay, so you see that it is not actually very straightforward. So it is not like this. So it is not straightforward that you have only edge or screw dislocation here, because it is the boundary here in the liquid does not look like this, right? So you don't have steps like that. And also in reality we see that even in solids, so dislocations are present in solids. It's a concept for solids, it's not a concept for liquid, but you can imagine it as, laminar flow of layers of liquid flowing above each layer in a very, very viscous liquid, right? So what I'm trying to say here is that even in solids, when you see the dislocations in microscope, they don't look like straight lines, they look like this. Okay, and so the dislocation in reality is not always or rarely an edge dislocation or a screw dislocation. It's actually a combination of these two, so that it looks like a curved. Okay, and so this is called a mixed dislocation, the dislocation in reality which looks like this. And one of the phenomena of this mixed dislocation is to move from one plane to another plane. So in FCC crystals, you have the direction on which dislocation moves, so the Burger vector's direction usually is the direction where the atoms are close to each other, right? So atomically closed packed plane, direction will be the direction in which it is easier for the dislocation to move. Okay, and in FCC that direction is 110. Okay, because on FCC you have atoms closer on the faces. So when you draw FCC crystal, you have on faces atom here, here, and at all the corners. So if you take this plane, on that plane also you have an atom at the center of the face. Okay, so on the faces, on the six faces of this cube, you have atoms sitting closer to each other in comparison to the plane if you take, which is like this. Okay, so this plane. So on this plane you don't have atoms, so you have atoms only there and also here. Okay, but if the dislocation has to move there, this distance is longer than that distance on this face plane. Okay, so that face plane, which is 110, is the plane of slip. Okay, and the closed packed direction is the, sorry, this is the direction of slipping because the atoms are closer there, and the plane on which they slip is 111 plane. So 111 plane, if you take x1, x2, x3 like that, okay, and then make a cube which looks like this, then 111 plane will be this family of planes. Okay, so that will be, and you will have many that kind of planes in this cube. So 111 plane is the plane of slipping and 110 is the direction of slipping in FCC, right? And then let me go to, so now we know in FCC it moves on 111 plane and the direction is 110, the family 110. So it could be 1 bar 0 or 1 0 1 1 0 1 bar. All those combinations of directions are possible, and all the possible direction of all the possible coordinates of planes are also possible. So 1 1 1 1 1 bar 1 and all those combinations of planes. Okay, so the family of planes is 111 and the family of direction is 110 on FCC. Now imagine that there are two 111 planes which are inclined in this way. So this is one type of 111 plane, and this is another plane which is 1 bar 1. Okay, and they intersect at some point of time, and the plane of intersection, so this is 111 plane, this is another family of 111 plane. Okay, and the direction along which the edge dislocation can move is 1 bar 0 1. Okay, so that's the direction where it can move. Now you have a dislocation loop. Okay, this dislocation loop, and the dislocation loop is such that here and here, let's call that A and B, these two are pure edge parts. So pure edge dislocation parts. Okay, and here and here you have pure, and rest of the things are a mixture of edge and screw dislocation. Okay, and this whole loop is moving. Okay, and they are moving, and then it may appear that after some point of time this dislocation, so because the screw dislocation can actually move in another plane. Okay, screw dislocation can move from one plane to another plane. So you will have to understand this part, because screw dislocation, so let's say this is my screw dislocation. Okay, and this is the line of screw dislocation, and it is moving in this direction like a helix. Okay, it is moving like that. Okay, so it doesn't require a plane to move. It is a line which is moving in the line, so it doesn't need a plane. But edge dislocation, if this is the line, then the Berger vector has to be perpendicular to this. Okay, and therefore edge dislocation needs a plane to move. So it can move only, and if this is x1 and this is x2 direction, then this edge dislocation can only move on x1 x2 plane. So it requires a plane to move. Screw does not require a plane to move. Edge requires a plane to move. Okay, so what happens here is that because a screw does not need a plane to move, it will just go to another plane. Okay, it will just pass on to another plane, right? And then slowly the whole dislocation will, so it may look like this, and then it glides along this plane, and then it comes back to the same plane again. So same plane meaning a parallel plane of the same normal vector, but at a certain distance. Okay, so then this dislocation loop has actually moved like this. Then after some time, the whole dislocation loop will be on this plane, So this dislocation loop would have crossed and come back to another parallel 1 1 plane. And this phenomena, when this whole dislocation loop moves here, is called double cross slip. And this part, so when it moves from this plane to that plane, is called cross slip. Okay, and cross slip, I have tried to explain a little bit here, but the phenomena is more complicated. It's just that, you know, screw part of the dislocation needs no barrier, no plane, so it can actually just go there. Edge part of the dislocation will not be able to go. Okay, so there has to be something here so that the whole thing passes on. Okay, and so this requires a little more explanation, which we will do later on.